Welcome to the Chemistry and Physics section of Test 1. In Passage 1, we'll be going over questions 1 to 5. So Passage 1 is saying, in order to understand the chemical evolution of life, scientists have studied the production of amino acids under conditions that simulate those of primitive Earth. Malic acid is thought to have formed via hydrolysis of a cyanohydrin intermediate, and the mechanism is kind of shown in Scheme 1. So we have this aldehyde on the left reacting with cyanide, and then it gets attacked because cyanide acts as a nucleophile and attacks this electrophile, which is our aldehyde. Then we have this new bond formed over here in the reaction product, and then water comes and reacts, turns the cyanide over here into a carboxylic acid. And then finally we have an elimination type reaction, and we see that this OH has been removed. It used to be over here. Now we have this double bond, and we get fumaric or maleic acid. So those are the steps involved in this scheme for forming maleic acid from compound A. Subsequent dehydration of malic acid results in the formation of fumaric acid and its cis isomer maleic acid. So malic acid was over here, and then we're told that dehydration forms either fumaric or maleic acid. So these are two different isomers, but otherwise they're similar. They came both from malic acid. Ammonia was thought to be a constituent of the early atmosphere, and it was proposed that it reacted with fumaric, maleic, and malic acids to afford a pre-biological synthesis of aspartic acid, which is another amino acid. So here in Scheme 2, so this is an amino acid. So the compounds that we made before, or malic acid, can react with ammonia, and now we see aspartic acid being formed. That is Scheme 2. In an attempt to verify this hypothesis, chemists tried to reproduce the synthesis of aspartic acid under simulated primitive Earth conditions. So an open flask containing malic acid was treated with a continuous ammonia feed, and the mixture was heated at 150 degrees Celsius for 1.5 hours. The experiment was repeated with a mixture of fumaric and maleic acids. The results were analyzed by paper chromatography. The RF values of the reaction mixture were compared to the RF value of a standard sample of aspartic acid. And I note RF is the distance moved by the compound over the distance moved by the solvent front. So that's the passage. Now let's get to the questions. Question 1 is asking us, in a chromatography of the reaction mixture, water absorbed on cellulose functioned as a stationary phase. What was the principal factor determining the migration of individual compounds in the sample? So we're talking about chromatography, and we were discussing RF. So you should know that what's taking place is thin layer chromatography, or TLC, and that's usually done on a thin strip of paper. You have a stationary phase, and the compound is spotted onto the stationary phase. It adheres to it to some degree, and then we run a mobile phase through the strip of paper. It goes up and it pulls along the compounds, and if they stick better to the stationary phase, they'll remain near the bottom where they were spotted. Otherwise, they'll be carried up the paper by the mobile phase. And we are told that the stationary phase here is water absorbed on cellulose. That is our stationary phase. So what determines migration of compounds? So once again, it's the difference between adherence to the stationary versus mobile phase. So in this case, since we use water and cellulose, both of those are polar compounds. Both of those have OH groups. So water is OH2, and then cellulose will have a lot of OH groups that are able to hydrogen bond. So it seems like the main thing which is going to have a compound sticking to the polar phase is going to be if it's a polar compound, and especially so if it can form hydrogen bonds, and it's going to really stick well to the stationary phase, whereas the mobile phase, which is going to be nonpolar in this case, will attract nonpolar compounds. But a key intermolecular attraction is going to be option A, hydrogen bonds. If you have hydrogen bonds forming, then that's going to be a key determinant in determining the final RF of the compound. So hydrogen bonding is the correct answer here. It's not solute concentration, that doesn't really matter, like the amount of the solute that we spotted onto the TLC, that doesn't really matter, because what matters really is the intermolecular forces between the stationary and mobile phases and the solute. So you just need to spot enough that you can visualize it when you see the results, but it doesn't change your final results. The stationary phase concentration also does not change your results. Once again, it's dependent on the interaction between these two things and not the concentration. You should just have, like a lot of stationary phase, like enough that you can run a proper column. And finally, D, the thickness of the paper does not matter either. We are running up and down a paper, and once again, it is based on intermolecular forces, so thickness of the paper does not play a factor in determining RF. So A is the correct answer here. In question 2, we're asked what assumption is being made if scientists conclude that aspartic acid was formed by the pre-biological synthesis in the passage. So there has to be a key assumption being made. If an assumption is made, that means that it's something that is not explicitly said by the authors, but it's something you have to accept for the next part of what they state to be true. So the authors want to conclude that aspartic acid was formed by the pre-biological synthesis in the passage. They were trying to test. They have this scheme 2 over here, and they're saying that scheme 2, aspartic acid, how it was formed in this primitive earth condition, was by taking either malic acid or the two isomers that are formed from the dehydration of malic acid and reacting them with ammonia. That could give us aspartic acid. And then they want to verify this. So right here is they try to reproduce the synthesis of aspartic acid under simulated primitive earth conditions, and then like if they actually do get aspartic acid formed, that will confirm their hypothesis. But the assumption that they're making is that this is how aspartic acid was made in primitive earth conditions, which means that malic acid must be available, ammonia must be available, and fumaric and maleic acids must be available. And fumaric and maleic acids are made initially from this compound, compound A, and then cyanide. So everything that's going on in schemes 1 and 2, they're assuming that they're available on primitive earth in order for aspartic acid to actually be made using this pathway. So that is the assumption that they're making. Option A is saying aspartic acid is unstable at temperatures below 150 degrees. No, the experimenters, it says at the end, final paragraph, that they did heat the mixture for 150 degrees, but this is most likely because they're trying to simulate how high the temperature was under primitive conditions. They're not just saying aspartic acid is unstable at those temperatures. If aspartic acid was... No, they're not saying that aspartic acid is unstable at temperatures below 150 degrees, because aspartic acid is a pretty common amino acid. Just from your knowledge of amino acids, you should know that it exists in us. And our body temperature is around 37 degrees Celsius. And so aspartic acid is definitely stable at temperatures below 150 degrees Celsius. They just use that temperature to simulate the temperature of primitive Earth. Option B is saying all the malic acid underwent the dehydration reaction to form fumaric or maleic acid. No, that's not correct. They're not assuming that all the malic acid, like over here in this step, they're not assuming all of it undertook this step and became fumaric or maleic acid, and then only that went on to become aspartic acid. No, because they're also saying that in scheme 2, malic acid itself could be a source for aspartic acid. So B is not an option, or it's not a correct assumption. It's not something that they even assumed. And finally, option C is saying compound A and cyanide were available on primitive Earth. Yes. So just like I explained, for them to assume that scheme 2 is what gives rise to aspartic acid, they're assuming that everything that's a reactant has to have been present under primitive Earth conditions. And option D now is saying the reaction between ammonia and fumaric acid was catalyzed by the presence of water. No. Here they just wrote, like they wrote the fumaric acid, they wrote ammonia. There's nothing given about catalytic acid anywhere really in this passage, so that assumption, that option doesn't really make any sense, so we can remove it. So C is the correct answer for question 2. In question 3, it says, according to the developed chromatography plate shown below, what is the approximate RF value of aspartic acid? So we're looking for the RF value of aspartic acid, and we are given a TLC plate here. You were told at the end of the paragraph that the RF is how far the solvent front moved. Sorry, how far the spot you're concerned about moved, divided by how far the solvent front moved. But this is something you should already know based on your knowledge of different chromatography types. And we're told over here on the left, this is our aspartic acid standard. So this spot, which is present in both the standard and then the actual mixture that they did, so we can tell that aspartic acid was formed based on the experiment that they did. But either way, we're told that this spot is where aspartic acid is. So we see how far that moved, which is around here. So 2, approximately around 2. And then the solvent front moved up to 10. So that simply means that 2 divided by 10, or 0.2, so 0.2, that is approximately how far aspartic acid goes. That's the RF of aspartic acid. So A is correct for question 3. It's simply knowing how to find the RF of a spot. In question 4, we're asked which of the following statements does not correctly describe the dehydration of malic acid to fumaric acid and maleic acid. So here are some statements. Some of them are correct. Which one is not correct? And then dehydration of malic acid. So that is given to us over here. Malic acid is dehydrated. So the main thing that happens is this OH, and then also one of the hydrogens over here is removed, and then this double bond is formed. So it's a dehydration reaction, meaning water is removed, and then we have this double bond formed. We're told that we get fumaric acid and maleic acid. And notice how there's a double bond, but it's drawn out as a straight chain. But you know that double bonds, they don't exist like that. They exist either like this, with the R groups on one side, meaning they're cis, or they could be trans. So there's nothing really selecting for whether we get the cis or trans isomer, but that's why we're told we get both fumaric and maleic acids. And we are told that we get fumaric acid, and then its cis isomer, which is maleic acid, so maleic is a cis form. We're told that we get both of them, and it's not fully told, but you can figure out that fumaric acid must be the trans type. So that's the main thing that we can see about that reaction. So option A is saying the reaction occurs most readily with tertiary alcohols. Well, if we are talking about if we're talking about like an E1 reaction, sure. Yeah, sure, why not? It could occur readily with tertiary alcohols. That's not something that's really incorrect. Option B is saying the reaction involves loss of water molecule. That is, yeah, what the definition is of a dehydration reaction. Option C is saying the reaction has a carbocation intermediate. So yeah, we must be talking about SN1 in this case. So SN1 is where you have a leaving group leave on its own, and then we have the carbocation intermediate, and then later on the double bond is formed. So what happens in this case is, first of all, the OH group leaves, and then later something comes and takes that second hydrogen, and then the double bond has formed. So yeah, we are speaking about an E1 reaction, not an E2 in this case. And also, we're under like a lot of like high temperature and pressure and everything. So yeah, E1 makes sense. It would go forward. If it's high temperature, that can drive off the leaving of an OH as a leaving group. So yeah, it makes sense. So SN1 can happen. Sorry, E1 is what's going on, because that's what option C is implying. And also E1 would, yes, occur most readily with tertiary alcohol. So A and C kind of go hand in hand. And option D, you definitely know, is incorrect. So even if you can't really tell whether it's an E1 or E2 mechanism leading to that dehydration reaction, you should be able to tell that D is incorrect, because D is saying the reaction is stereospecific, and what that would mean is that you specifically get one isomer as a product. But since we're not just getting trans or cis, we're getting a mixture of both. We can't say that the reaction is stereospecific, so you should definitely see that answer option and know that it's an incorrect statement and then choose it. So D is the correct answer here. And in question 5, we're asked what type of functional group is formed when aspartic acid reacts with another amino acid to form a peptide bond. So aspartic acid is an amino acid, and then when it reacts with another amino acid and forms a peptide bond, what is that? So a peptide bond looks essentially like this, and then there'll be like some R group as well. and that is also called an amide group. So that's just another name for a peptide bond is an amide bond, because that type of carbonyl is an amide. It's not an amine. That would just be like a nitrogen attached to an alkyl chain. It's not an aldehyde. Aldehydes look like that. It's not a carboxyl group because they look like that. So it looks like this with a nitrogen. So a peptide bond, another name, is an amide bond. So that's the correct answer for question 5. Questions 6 to 9 are related to passage 2. The passage is saying that the nucleophilic alkyl substitution reactions are among the most thoroughly studied transformations in organic chemistry. A substitution by an SN2 reaction mechanism is shown in figure 1, and a substitution by an SN1 mechanism is shown in figure 2. So over here we see an SN2 mechanism, and it's bimolecular, meaning both the nucleophile and the electrophile are involved in the rate determining step. So here we can see the nucleophile coming in, attacking that electrophile carbon, and then at the same time the leaving group is kicked off, and then we can see it, the free leaving group over here in the product side. That's the SN2 reaction mechanism. The reaction mechanism for SN1 is now over here. In that, first of all, the leaving group leaves, and then it's a free leaving group. We have a carbocation with that positive charge, and then the nucleophile comes, reacts with the carbocation, which is our electrophile, and then we get the nucleophile added over here. And first step was a slow step, second is fast. And with SN2 reactions, you should know there's always an inversion of stereochemistry. So for example, if it was R before, now it's S in the product. Whereas for SN1, we get both of the isomers being formed because we have a planar intermediate. The SN2 mechanism involves a direct displacement of a leaving group by a nucleophile. The reaction results in an inversion of configuration at the carbon bearing the leaving group because the incoming nucleophile attacks it from the side opposite the leaving group. The SN1 reaction mechanism involves an intermediate carbocation that is formed by loss of the leaving group. The nucleophile can react with the planar carbocation from either side, leading to the inversion or retention of the configuration at the site of the substitution. The product distribution of two reactions is shown in figure 3 and 4. So here we're seeing an SN2 reaction because we have a primary carbon over here, and then we're reacting it with some acid, which is catalytic, and then we have like either chloride or bromide as our nucleophile. And here's the distribution of products we see. We see 70% attack by the bromide, 30% by the chloride, and then the water is the leaving group, which was this OH here at the beginning. That's an SN2 reaction. And then over here in figure 4, we see an SN1 reaction. And in this, first of all, the OH will leave because, once again, we have an acid. What changed here is the carbon at which the attack takes place. Now it's a tertiary carbon. This is much more likely to undergo SN1 because we have a more stable carbocation that's formed. So the OH leaves, we have the carbocation. We have the same reactants though, the chloride and bromide. Now we see a more even distribution. 40% bromide, 40% chloride. So those things are equal in terms of how much product they make up. And then we also see that we get 20% of an elimination reaction going on here. So that's another thing which begins to be a significant factor as well. We're told that the rates of the reaction shown in figure 3 increases as the concentration of alcohol, halide, or the acid increases. The rate of the reaction shown in figure 4 increases as the concentration of the alcohol or the acid increases. The reaction is independent of the halide concentration, and this is simply because it's either a unimolecular or bimolecular reaction. Now let's get to the questions. In question 6, it says if 2-pentanol replaces 1-pentanol in the reaction shown in figure 3, the rate of substitution is going to be less because of what? So we're saying 2-pentanol is used now instead of 1-pentanol, and there's less substitution. Why is that? So here's the reaction. Before you had 1-pentanol, so that means that the OH group was at the end. But now if we take this molecule, so at the second carbon, there is now an OH group, there's less of a reaction. Why? It's because this carbon went from being a primary carbon to now being a secondary carbon. Over here before we just had 2 hydrogens. So when our nucleophile is coming in and attacking that carbon, it has more space to reach the carbon, meaning there's less steric hindrance. Whereas now we have this entire group to also worry about So there are like 3 hydrogens over here on that carbon, and then there's all of this alkyl chain as well. So the nucleophile has to worry about those in order to get to this carbon that it wants to, which is the electrophilic carbon. So that's because there's more of a steric hindrance. That's why there's less SN2 taking place. And also keep in mind that SN2 has to happen from certain specific angles. So it's a backside attack. It comes from the opposite side of where the leaving group is. And so it's harder to come at the electrophile from those angles if we have more steric hindrance. Option A is saying there's less substitution because the CO bond in 2-pentanol is stronger than the CO bond in 1-pentanol. That's incorrect because it's talking about the CO bond. In both of them, it's just a carbon hydroxide bond. Like that bond is the same. The position has shifted, but there's nothing inherently about that bond that's different. Like it's not like we have a double bond versus a single bond or anything. Those bonds are the same, so this option is incorrect. Option B is saying there's a competing elimination reaction that slows the rate of substitution, but we're shown over here that, the elimination reaction, the E2, it wasn't really a significant factor over here. We're shown that it is a significant factor when it's a tertiary carbon, but we made a secondary carbon, so if we can find something that is a stronger answer, that would be better, because we don't have enough evidence to say that now the competing elimination reaction is significant enough. We don't have enough evidence for that. Option C, there is more steric hindrance at the oxygen atom in 2-pentanol than in 1-pentanol, making protonation less likely. So that's incorrect because it's saying steric hindrance at the oxygen atom, but D is correct because it's saying there's more steric hindrance at the 2 position, meaning the 2 carbon of 2-pentanol, than at the 1 position of 1-pentanol. So D is the correct answer because it's talking about carbons, so that is what we're looking for at steric hindrance. And once again, B is not correct because we don't have enough evidence saying that there's a competing elimination reaction. That would be more likely if we were talking about a tertiary carbon, or if we were talking about changing up the reaction conditions, because you can change up, for example, the solvent to make elimination more favored or something like that. But we didn't change anything like that. We just changed where the OH group was on the molecule. So we don't have enough evidence for B. D is the correct answer here. In question 7, it says if reaction 2, which is in figure 4, is repeated with HCl and the compound shown below, which of the following compounds is not a direct product? So we are doing reaction 2, and if you go back to figure 4, you see that this reaction with a tertiary alcohol was an SN1 type reaction. So that means that we can get either displacement of the OH with the nucleophile, so either bromide or chloride, or we can get an elimination type reaction happening. So if that reaction is repeated, so tertiary alcohol with those reagents, with now HCl and this compound that's given to us, which is not a direct product without some kind of rearrangement. So if we use this and we react it with HCl, what can we get? Well, once again, we have a tertiary alcohol. So this could potentially leave, and then an elimination reaction would be, for example, if chloride did this, we can get a double bond forming here. We could also get one forming here, or we could get a double bond forming here. So the only places that a double bond can form is if the carbon next to where the OH is loses a hydrogen, and then we have a double bond between that initial electrophile carbon and the carbon next to it. So we can get it at the 3 positions which I've highlighted, but not anywhere else. Like, for example, it doesn't make sense to have a double bond forming there because the leaving group is too far away. And then next we could have the carbocation formed and then this replaced with the chloride. So those are the options that we could have. We're looking for what is potentially not possible, and A is correct. Because if the carbocation was here, we could have like a hydrogen from here coming in, we could have a hydrogen from here coming in, but it doesn't make sense for a hydrogen to come here because then there needs to be a leaving group over here at this carbon, but now this carbon has too many bonds. This carbon has 1, 2, 3, 4, 5 bonds. That's too many bonds. That double bond is too far away from where the leaving group was. It doesn't make sense that this product is formed, so this is our correct answer. Option B is fine. It's fine if a double bond is formed over there. Option C and D are the different enantiomers, so they're fine too, or there would be diastereomers because it just changed at one stereocenter. But either way, these two isomers are fine because it's just saying that there's a carbocation formed, and then the chloride can come and either retain or flip the stereochemistry, retain or invert it. So both of those are fine because they're both happening at the actual carbocation site. So yeah, those are potential options for products that we can get. So A is the only one which does not logically make sense, and so it's a correct answer for question 7. In question 8, it says if a solution containing the compound shown in figure 4 is injected into a gas liquid chromatograph, the first peak observed in the GC trace is attributable to which compound? So the compounds in figure 4 are in a gas liquid. We do gas liquid chromatography on them. The first peak is which one? So what you need to know about gas liquid chromatography is that what we do is we have like a solution of something, and then we heat it up and we make it volatile enough that it turns into a gas. So we go beyond its boiling point, turn it into gas, which means that the first thing that comes out is the one with the lowest boiling point. So it turns into a gas first, it comes out, that's our first peak, that's the thing that we collect first. And then the last peak is going to be the one with the highest boiling point, the one that it took the longest to evaporate. So of these compounds, we have this, the actual like starting reagent, which would be an alcohol, and then whenever you see an OH thing, like any molecule with an OH, you know that a solution of it can have hydrogen bonding, and so it's going to have a pretty relatively high boiling point. So of these compounds, this would be the highest, which means that it's likely to be the last peak. And then the other ones, bromide and chloride, these molecules have a dipole because of that carbon bromide or chloride bond, and so dipole-dipole interactions are going to make more intermolecular attractions, so attractions between different molecules in the solution of this compound, which is going to raise the boiling point. The one which has the lowest boiling point is going to be this one because it's just carbons and hydrogens, and like it has some van der Waals interactions, but all of the other compounds have the same amount of carbons, so they have similar van der Waals interactions, but the dipole and the hydrogen bonds are stronger in intermolecular attraction, so it gives them a higher boiling point. So that double bond one is the lowest. And so for question 8, B is the correct answer. This butene, the ene was the double bond one, that compound is going to have the relatively lowest boiling point, which means it's going to be our first peak. This butanol is an alcohol, so it is going to have the highest boiling point. And then the chloro compound and the bromo compound are going to have the dipole interaction, so they are not going to be the first peak. That's it for question 8. In question 9, we're asked what is the product of the reaction of compound 1, which is shown below, with HBr by the pathway shown in figure 3. So compound 1 reacts with HBr with the pathway shown in figure 3. So in figure 3, that was down here. It was an SN2 type reaction. So we're asked what is the product here. So since it's a primary alcohol, it's going to be an SN2 reaction. And remember, we said with SN2 reactions, you have the nucleophile coming in and doing a backside attack. So from the opposite side of where the leaving group is, which means that once the once the nucleophile comes in, it's going to invert the stereochemistry. So all we really need to do is find out what the stereochemistry of this compound is, and then the opposite of that will be the stereochemistry of the product. So we just need to use our Kahn-Ingold Prelog rules, and the highest priority is the one with the highest atomic number. So attached to this carbon would be the oxygen first, then after that would be the carbon, so that would be second, and then between hydrogen and deuterium is higher priority, so that would make deuterium number 3, hydrogen number 4. And then we just go from 1 to 3, and that ends up taking us in a clockwise direction. And since our lowest priority is in the back, we keep the stereochemistry, otherwise we would flip it. But we see that it's clockwise, meaning it's R. So the stereochemistry for compound 1 is R. And then if we have an SN2 reaction, that means that the product is now going to be S. And then where is the product going to attach? We're reacting it with HBr. So Br is going to come and attach to this same carbon, and then the OH is going to be removed. So it's going to be attached to the same carbon. I haven't drawn the stereochemistry properly, but it's attached to that carbon 1. So we're looking for something that is S and not R, and we're looking for something that has all the labeling properly as well. And how many carbons are there in this molecule? There are 1, 2, 3, 4, 5. So 5 carbons in this molecule. That means option B is incorrect and C is correct. So it is S, 1 bromo and 1 deuterio. So both of those things are at the 1 carbon. And then it's a pentane, so it's a 5 carbon molecule. So once again, 1, 2, well actually we would start from over here. So 1, 2, 3, 4, 5. So the lowest number goes to the highest priority group. So start from the right side, but it's a 5 carbon molecule. Option B was saying that it was 6 carbons, so that would be incorrect. So C is the correct answer here for question 9.
In question 10, it says that acetic acid and ethanol, they react to form an ester product as shown below. So we know what happens here is this alcohol is going to be our nucleophile. Our electrophile is a carboxylic acid. And so we're going to get attack at the carbonyl carbon. This oxygen double bond breaks open and then comes back down to kick off the OH. Our product then is this ester, and then the OH left as water, because this hydrogen over here, it got transferred to the OH group of the carboxylic acid. That's our water. So we get ester and water. In determining which reactant actually loses their OH group, so we see that the carboxylic acid had an OH group, and then so did the alcohol. If we want to figure out which OH group was lost, which type of isotopic substitution would be most useful. So we want to replace one of these molecules with its isotope. So an isotope meaning we change the number of neutrons, but we don't change the number of protons. Well, if we want to figure out which OH group is lost, what we should do is change the oxygen. So right now, the isotope that we have most of is oxygen 16. So if we change it to another isotope, such as oxygen 18, and we do that for both of or either one of this oxygen over here, so make it oxygen 18, or this oxygen, then we can determine which compound actually lost their oxygen. Because if, for example, the oxygen here is oxygen 18 labeled, and then we see at the end that this one is also 18 labeled, then we can tell that, okay, the alcohol still has its oxygen. We should do that for oxygen because the carbon-oxygen bond does not break. However, this oxygen-hydrogen bond, it's much weaker, and it breaks and is reformed all the time. So if you had a solution of carboxylic acids, the hydrogens are exchanging all the time. So you don't want to replace the hydrogen with an isotope, because even if you replace it with an isotope, that isotope in solution could be exchanged with something else. So a hydrogen of the solution, and that's probably the most common form of hydrogen. So that's why your isotopic change would be lost. So option A for question 10 is saying replace the acidic hydrogen of acetic acid with D. That's incorrect. So is option B, because you do not want to replace any of these hydrogens. Option C is that we replace the carbonyl oxygen of acetic acid with O18. So it almost seems correct because we're replacing oxygen, but they're saying the carbonyl oxygen. The carbonyl oxygen of acetic acid is this oxygen over here. And if you know the reaction mechanism, you know that this is not the oxygen which is lost. It breaks its double bond, and then immediately the tetrahedral intermediate is going to collapse and the oxygen is going to come back down and form another double bond. So the carbonyl oxygen, we already should know that it's not lost. Therefore, you should replace the hydroxyl oxygen of the either acetic acid or the alcohol. So that's why D is the correct answer, because that is what they propose to do. Moving on to question 11. A person whose eye has a lens to retina distance of 2 centimeters can only see objects that are closer than 1 meter away. What is the strength of this person's eye lens? And in this question, they already tell you to use the thin lens formula. Even if they didn't, you should know to use this formula for when you're talking about this lens to retina distance, and then also the distance of objects that you can see, and of course strength as well. So how do we find this out? Just do 1 over the values that they've given us. So 1 over 1 plus 1 over 0.02. That means that we have 1 plus 50. So both of these were equal to S, and so 51D is what we should get for S. So that's why C is the correct answer. So for question 11, you essentially just have to use exactly the formula they gave you, use the values that they gave you, do it in terms of meters, and then figure out what S is. It's not negative, and it's not any of the other number values. Moving on to question 12, we're asked which statement correctly describes how enzymes affect chemical reactions, and they do it through stabilization of what? So for enzymes, if you are studying for the MCAT, this should be hammered into your head by now, that enzymes, they lower the activation barrier of a reaction, so that's how they get the rate to increase. They don't affect the thermodynamic properties like delta G, so the change in free energy, they don't affect that. And they also stabilize the transition state. So by stabilizing the transition state, since that is stabilized, the substrate, it goes and is converted to the transition state, and then that transition state goes on and becomes a product. So option A is saying that the substrate changes, stabilization of the substrate changes the free energy of the reaction. That is wrong on both accounts. We're not stabilizing the substrate, we're not changing the free energy of the reaction. So wrong, incorrect, definitely do not choose option A. Option B is saying stabilization of the transition state changes the free energy of the reaction. So first part's correct, second part is not. We don't change the free energy. Option C is saying stabilization of the substrate, once again. Now they're saying changes the activation energy of the reaction. Now the second part of the answer is correct, but we don't stabilize the substrate, we stabilize the transition state. If we stabilize the substrate, the enzyme and the substrate would just be bonded, and then the reaction wouldn't really go forward. D is the correct answer. We stabilize the transition state, and then this changes the activation energy of the reaction. So that's how enzymes work.